In this video, we continue the triple integrals, but in here we have other kinds of coordinate systems that can be used for the solids or the volumes, which are easier to describe in terms of other coordinates. One of the other coordinates in the in triple integrals or for triple integrals. One important coordinate system that we can use for triple integrals is cylindrical coordinates. Cylindrical coordinates. Before talking about the triple integrals in the cylindrical coordinates, let's see how we show a point in the three-dimensional space using cylindrical coordinates. Somehow it is similar to the polar coordinates in 2 dimension, but of course here we have 3 dimensions. Suppose the x-axis is the axis sticking out of the screen. So since I want to draw something in three-dimensional space, that's why I should make this assumption. So x comes out, y is this horizontal axis, and the z is this horizontal axis. I'm sorry, this vertical axis. So x sticks out. So a point P in the space will be in the cylindrical coordinates will be denoted by three things: r, theta, and z. Suppose I project P on the xy axis, on the xy plane, sorry. I project P on the xy plane. And if from the center or from the origin, I connect the origin to here, this angle is theta, and this length is r. Very similar to the polar coordinates, but here we have 3 dimensions. Suppose when we project this on the z-axis, this is the value of z. So these are the 3 coordinates that specify a point in the cylindrical coordinates. Some surfaces are easier to describe in using cylindrical coordinates, and especially the solids which have been enclosed by those surfaces. Suppose the solid or the volume that we have looks like a cylinder. A cylinder. I'm looking from the top, so this is the top base of the cylinder. This is the lower base. Let me make this part in the dotted lines. So we are looking to this cylinder from the top. And suppose this is in the XYZ coordinate. Let me first draw a Z axis here. This is X. This is Y. So imagine that the lower point on the z-axis is 1 and the upper point is 4. And suppose the radius of this cylinder is 2. So if this is the radius, suppose this radius is 2. If I want to describe all the points on and inside this cylinder, so it's a solid, it's a volume. It's not just a surface, it's the surface and inside this surface. So from the top and the bottom, it is bounded by the bases of the cylinder, and from the side, it is enclosed by the cylinder itself. So the solid inside the cylinder can be described by obviously Z is between 1 and 4, so Z is between 1 and 4. The distance from the z-axis runs from 0 to 2. All the points inside the cylinder, the farthest away is 2. Those on the x-axis, for them R is 0. So R is from 0 to 2. And this cylinder goes all the way around z-axis, meaning that in every direction, for every angle from 0 to 360 degrees, or in terms of radians, from 0 to 2 pi, we have theta. So theta is from 0 to 2 pi. If I say that theta runs from 0 to like just pi, not 2 pi, that will be vertically half of the cylinder, not the entire cylinder. But from 0 to 2 pi gives me the entire cylinder. So describing inside this cylinder, or the solid which is identified by this cylinder, is much easier to be explained or described in the cylindrical coordinates rather the Cartesian or XYZ coordinates. Okay, now let's see how this plays out in the case of the triple integrals. So as a note, suppose a solid is described by theta is between two angles, R is between two numbers, and Z is between two numbers. So this describes inside the cylinder. Then this triple integral over this region, let me show the region by R, but that R, so the region R, but that R can be described as Z runs from C to D. So the inner integral I can choose from C to D. The distance from the central axis Z is from A to B, and the angle goes from alpha to beta. Usually the function that we have, let me call the function G, will be in terms of theta, R, and Z. And then we have, similar to the triple integrals for the Cartesian case, dV, the infinitesimal of the volume. This volume dV, this infinitesimal volume, in terms of d theta, dr, and dz, can be described as r dz dr d theta. You might remember that in the polar situation, there was an extra r before dr, the same similar situation here. So this, the product of r dz dr d theta, in fact, is dv. So this triple integral. This is a triple integral in the cylindrical coordinates. One physical example for such integrals is if this function g at any point gives us the density of the solid. By calculating this triple integral, we find the total mass that object has. In the case that g is 1, constant 1, the triple integral will gives us the volume of the solid. So, in fact, as I just explained, the triple integral of dv, so that's meaning that here it is just 1, the function is 1, is the volume of the solid. Okay, let's do a couple of examples. That's what we are supposed to do in this topic to be able to calculate triple integrals in this coordinate system, the cylindrical coordinates. Example, calculate the triple integral from 0 to 2 pi. R runs from 0 to 2 and Z runs from 1 to 4. That's exactly the cylinder that I discussed um, a few slides ago, dV. In fact, the function involved is just function 1, one constant 1. That's why we don't see the function here. So first of all, let's see what is dV in terms of dz dr d theta. So the integral theta runs from 0 to 2 pi, r runs from 0 to 2, and z runs from 1 to 4. dv is what? R dz dr d theta. So first we do this integral, the inner integral. So the integral from the theta runs from 0 to 2 pi, r runs from 0 to 2, dr d theta. I just want the inside. For that inside, antiderivative of r with respect to z. The integral of r dz is like r is a constant, and we're integrating with respect to z. So it's rz, right? With respect to z, r is a constant. So that's going to be rz. And we should evaluate at the end points and do the subtraction. So what is this? This is r, so r times 4 minus r times 1. So we evaluate rz at z equals 4 and z equals 1 and do the subtraction. So this is r times 4, which is 4r, minus r times 1, which is r. So far what we have is the integral theta runs from 0 to 2 pi. R runs from 0 to 2 of 3r dr d theta. So 4r minus r is 3r. That's why we see here 3r. Now we have a double integral. We know how to deal with this. Now look at this integral inside. Antiderivative of 3r with respect to r is 3r squared over 2. So this is going to be equal to the integral from 0 to 2 pi, 3r squared over 2, and r runs from 0 to 2, and then d theta is the last integral, is related to the last integral that we need to do after this step. So what is this? 3r squared over 2, and r is 2 is 3 times 2 squared over 2. 3 times 2 squared over 2 minus, and r is 0, 3 times 0 squared over 2. 3 times 2 squared over 2 is just 6. And the other term is 0. So far we have the integral from 0 to 2 pi of 6 d theta. Antiderivative of 6 with respect to theta is 6 times theta. Then I need to evaluate at 0 and 2 pi and do the subtraction. So 6 theta evaluated at 2 pi, and then evaluate at 0 and do the subtraction. So 6 theta. 6 times 2 pi is 12 pi. 6 times 0 is 0. So the final answer is 12 pi. Okay, let's see another example. In the next example, we have the same region in the three-dimensional space. Theta runs from 0 to 2 pi. R runs from 0 to 2. and z runs from 1 to 4. This time the function is not just 1. In this case, it is 10 times r squared. Okay, first of all, let's remind ourselves that in the spherical coordinates, what is dv? So dv is what? dv is r dz dr d theta. So dv is r dz dr d theta. Okay, so theta runs from 0 to 2 pi. R runs from 0 to 2, and z runs from 1 to 4. 10r squared times another r, 10r cubed, right? dz dr d theta. So look at this integral that we should calculate first, the most interior integral, which is with respect to z. So for this integral, what I have is 10r cubed is like a constant with respect to z. So antiderivative of a constant is constant times the variable. So in this case, it's going to be 10r cubed times z. And I should evaluate at the limits of the integral with respect to z. So what is this? 10r cubed, and z is 4. 10r cubed times 4 for the r cubed. When z is 1, 10r cubed times 1, just 10r cubed. So the result is 30r cubed. So far I have the integral theta runs from 0 to 2 pi. R runs from 0 to 2. And that interior integral happened to be 30r cubed. Then we have dr d theta. Now look at this integral now. With respect to r, what is antiderivative of 30r cubed? 30 is a constant, and antiderivative of r cubed with respect to r is r to the 4 over 4. So this is going to be 30 r to the 4 over 4, and it should be evaluated at these limit numbers of the integral. So when r is 2, 30 times 2 to the 4 over 4. 2 to the 4 is 16 over 4 is 4. So 30 times that is 120. At 0, it's just 0. 0 to the 4 is 0. So this the value of this integral is 120. So let's see what we have so far. We have the integral from 0 to 2 pi. We just calculated that interior integral, which was 120 d theta. Antiderivative of 120 with respect to theta is 120 theta. And we should evaluate at the limits of the integral with respect to theta. 120 theta, when theta is 2 pi, is 120 times 2 pi, which is 240. minus 120 times 0, which doesn't affect two. I'm sorry, this was 240 pi. When theta is 2 pi, 120 times 2 pi is 240 pi. And when theta is 0, 120 times 0 is just 0. So the final answer is 240 pi.